Okay, so after looking at the problem solving procedure, step 0, you need to do some type of figure sketch summarizing the inputs and outputs of the problem. Then you need to do some type of figure from which you will be able to write down the equations in step 2. Okay? Then in step 2, you start solving the problem. If at the end of step 2 you are able to solve the problem, you go directly to step 4, which basically means solve numerically or symbolically the problem. If after step 2 you still need additional equations, you need to go to step 3, and you stay in step 3 until you have enough information in order to solve the problems. Okay, so let's try to take any problem. So I selected 3 problems to apply the procedure. So this is the first problem. So as you can see, this barometer shown in the figure contains mercury. If the local atmosphere is 100 kilopascals and G equal 9.81, so this is gravity, determine the height of the mercury column L in millimeters of mercury or inches of mercury. Okay, so this is the problem statement. So I know everything is clear, but just for the sake of the procedure, let's just redo the problem. Okay, and I put it side by side. So let's say step 0. So step 0, I look at the figure. Okay, so there's a tube over here. All right, so let's see. So the fluid in question that we are dealing with is mercury. So this is mercury. And you know that the density of mercury, so the chemical sign for mercury is Hg, so I use that one. It's 13.59 grams per centimeter cube. Okay, and then what else do we know? That the atmospheric pressure is 100 kilopascal, so that's the one acting all over here, over here. All right, and basically what is that we need to find? We need to find the height L over here. Okay, so basically L is what we need to solve for. All right, so this is step 0. So let's go to step 1. So step 1, what I would do here is that, okay, we need to find out what is L over here. So if I take one element of the mercury, let's say one element here, so the pressure would be the same everywhere, and let's say I move that little element here now, let's say over here. So what would be the figure that we'll have? Will look something like this. Okay, so if you look at this figure here, this one is connected to the P atmosphere. So I'll move that little element here like this, but this will look like here will also be equal to P atmosphere. Okay, so if you remember, pressure equal force over area. So basically it means that the force will be the pressure times the area. And the area here should be the area of the tube over here. But this will cancel out, so it's not a big deal. And now we need to find out what is the pressure created by this column of mercury. So maybe let me just expand it a little bit more, might be a little bit easier. So now, if we look at the gravity, it will be G. So it will be rho G times L will be the value of the pressure. If you remember, one of the fundamental equations of this chapter is pressure equal to rho GH. In this case, H equal L. Okay? So again, the force would be times A. Okay? So it will be the figure I would do to solve the problem. Step number 2, now you need to apply the fundamental equations. So over here, what is the fundamental equations to use is basically the static equation, summation of forces equal to 0. Okay? So basically, if I do here, this will be the direction of the force. We take this as being positive. This will give us what? P atmosphere times A minus rho GL times A equal to 0, which will give us the equation P atmospheric, after you cancel the area, equal to rho GL. Okay? So this is the fundamental equations that we have. Some of you probably knew that equation by memory, but I just try to give everything the fundamentals, okay, and show that really the procedure works 99.9% of the time. So in this problem now, maybe one step that we need to pay attention is that in our problem, G is equal to what? Is the density of the mercury. Okay, G is the gravitational force, and L is what we need to find. Okay, so in this problem, something that was given, and maybe I forgot to put, is that the value for the gravitational constant is 9.81 meter second square. Okay, so we got all the equations we need, so we got that equation. And now from here, are we able to solve for L? Or L will be equal to what? P atmospheric divided by density of the mercury times G. Okay, so in this equation, we know that the P atmospheric is equal to 100 kilopascals. We know the density of the mercury is equal to 13.59 grams cubic centimeters, and that G will be equal to 9.81 meters second square. So that means we got all the information. So we can go directly to step 4. So step 3, you don't need to write it down, but just for the sake of clarity, not needed. So we can go directly to step 4, which is to solve. Okay? And I will do that on the next page. So it will be step 4. Okay, and here I think we're going to have a bunch of unit transformation. So we can maybe remember or recall here the expression that we need to solve. P atmospheric density of mercury times G. Alright, so let's go ahead. So L will be equal to what? We know that the value for the atmospheric pressure is 100 kilopascals. Okay, and then dividing, we have a value of 13.59 grams per centimeter cube times G, which is 9.81 meter second square. Okay, so over here we have a bunch of unit transformations. So, okay, I don't know if all are going to fit on the one line. Let's just try. So, okay. So let's start by the top. And then we'll see what happens. So here we're gonna have 1 kilopascals. That would be equal to what? So one kilopascals equals 10 to the 3 pascals. Then we have that 1 pascal equal to 1 Newton divided meter square. And then we have that 1 Newton will be equal to 1 kilograms meter 7 square. So basically all this to do what at the end is that we see that we can cancel, so this would be 10 to the 3, then we can cancel, so this kilopascal, so this will really cancel this one over here. So at the end we have Newton cancel newtons. So this basically will give us kilograms divided by meter second square. And now the bottom one might be a little bit more complicated. So let's see. Unit wise, we have the gram that we want to transform into kilograms. So what do we have over here? We'll have 1 gram equal to 0.001 kilograms. Okay. Then we have that 1 centimeter is equal to what? 0.01 meters. But since you need to take that to the cube, you take everything to the cube. All right, and doing this, we're going to cancel this one here, this one here, this one here, and this one here. Okay. So okay, so this kilogram would cancel also with this one. So we have cubic meters divided by meters here and this meter. So we ended up with units of meter, which is good. Okay. So if you do this calculation, this will be equal to 0.75 meters. Okay. But in the problem, they ask us to find the result in what? In millimeters of mercury over here. So again, we need to do one more unit transformation. So we do 1 meter will be equal to 1000 millimeters. So at the end, we'll have that L will be equal to 700 millimeters. And because the density is the one of the mercury, we say 750 millimeters of mercury. Okay, in addition to this, we need to find the final result in inches per mercury. So one more unit transformation. So we have 750 millimeters. Really, the mercury should not be that important. And then what we have, so they want this in inches. So let's see, I know that 1 inch is 0.0254 meters, and then we know that 1 meter equals to 1000 millimeters. So if we do this, this will cancel this millimeters, this meter will cancel this one. So at the end, we will have that this is equal to 29.53 inches of mercury. Okay, don't forget here to multiply this one by 1000. All right. And this will be the end of the program.